scientists found a surprisingly simple way to create powerful quantum states. Source: University of Chicago Pritzker School of Molecular Engineering Research, published in Physical Review X. Quantum entanglement is often described as one of the strangest phenomena in the universe. It is a phenomenon so unusual that even Albert Einstein famously referred to it as spooky action at a distance. Yet despite its mysterious nature, quantum entanglement sits at the heart of some of the most promising technologies humanity hopes to build, from ultra-precise sensors and secure communication networks to powerful quantum computers capable of solving problems beyond the reach of today's machines. The challenge is that creating the highly entangled quantum states needed for these technologies is notoriously difficult. Researchers often require complex experimental setups, sophisticated hardware, and carefully engineered systems to produce and maintain these fragile states. Now, scientists at the University of Chicago may have discovered a surprisingly simple shortcut. In a new theoretical breakthrough published in Physical Review X, researchers have shown that a small modification to a common quantum optics system can generate a remarkable variety of powerful entangled states without requiring entirely new hardware. If confirmed experimentally, the discovery could significantly accelerate the development of quantum sensors, quantum simulators, and future quantum technologies. To understand why this matters, we first need to understand what makes entanglement so valuable. In classical physics, objects behave independently. If you know the state of one object, it generally tells you very little about another distant object. Quantum mechanics is different. When particles become entangled, they form a shared quantum state. Their properties become linked in ways that cannot be described by classical physics. Measuring one particle instantly provides information about the others, regardless of how far apart they are. This remarkable interconnectedness allows quantum systems to process information differently from conventional technologies. Quantum computers rely on entanglement to perform certain calculations exponentially faster than classical computers. Quantum sensors use entangled particles to achieve measurement precision beyond what would otherwise be possible. Many scientists believe entanglement is one of the key resources that will define the next generation of technology. The problem is that entanglement is extremely difficult to create and maintain. Researchers have spent decades developing increasingly sophisticated techniques to generate complex entangled states. Many of these approaches require elaborate control systems and highly specialized experimental environments. The University of Chicago team wondered whether there might be a simpler way. Their solution focuses on a well-established area of quantum physics known as cavity quantum electrodynamics, often called cavity QED. In these experiments, atoms are placed inside an optical cavity formed by highly reflective mirrors. Light becomes trapped between the mirrors and repeatedly interacts with the atoms inside. These atom-light interactions allow researchers to manipulate quantum states with remarkable precision. However, traditional cavity QED systems suffer from an important limitation. Because all of the atoms interact with the trapped light in essentially the same way, the system possesses a high degree of symmetry. While symmetry often simplifies physics, in this case, it restricts the types of entangled states researchers can create. The atoms become almost indistinguishable from one another, limiting the system's flexibility. The breakthrough came from finding a surprisingly simple method to break this symmetry. Instead of changing the overall hardware, the researchers proposed slightly shifting the energy levels of different groups of atoms. The concept is elegant. All of the atoms continue interacting with the same light field inside the cavity, but additional lasers or magnetic fields introduce tiny energy adjustments to selected groups of atoms. Each atom is paired with another atom receiving an equal but opposite energy shift. This subtle modification makes different groups of atoms behave slightly differently while preserving enough structure to keep the system stable and controllable. Remarkably, this simple adjustment unlocks access to a wide variety of highly entangled quantum states that were previously difficult or impossible to generate in standard cavity QED systems. Even more impressive, researchers can switch between different quantum states simply by adjusting the laser settings. No new hardware is required. In many cases, scientists could potentially implement the technique using equipment already available in existing quantum laboratories. The implications for quantum sensing are particularly exciting. Quantum sensors are among the most promising near-term applications of quantum technology. By exploiting entanglement, these devices can detect extraordinarily small changes in magnetic fields, gravitational fields, acceleration, and other physical quantities. Such sensors could improve navigation systems, geological surveys, medical imaging technologies, and even the detection of underground structures. However, there is a major problem. Entanglement provides exceptional sensitivity, but it is usually extremely fragile. Environmental noise can easily destroy the delicate quantum states that make these sensors powerful. This creates a difficult trade-off. The more sensitive a sensor becomes, the more vulnerable it often is to interference. The new approach appears capable of overcoming this limitation. The researchers demonstrated that a system containing two groups of atoms could function as an extraordinarily sensitive gradient detector. Imagine placing one group of atoms in one location and another group some distance away. The resulting entangled state becomes sensitive to differences between the two environments while naturally ignoring disturbances that affect both locations equally. In effect, the sensor can detect tiny variations in magnetic or gravitational fields while rejecting large amounts of background noise. This combination of extreme sensitivity and noise resistance is highly unusual in quantum systems. Another important advantage is practicality. Many advanced quantum states require specialized measurement techniques that are difficult to implement. The newly proposed states can be measured using standard Ramsey measurement methods already widely used throughout quantum physics. This greatly increases the likelihood that the approach could be adopted experimentally. The researchers also found
that their method can generate one of the most famous entangled states in condensed matter physics, the AKLT state. First proposed in the 1980s, the AKLT state has become an important theoretical model for understanding unusual magnetic materials and quantum many-body systems. Physicists have long been interested in creating and studying such states because they provide valuable insight into how complex quantum systems behave. Some researchers even believe these states could play a role in future quantum computing architectures. The ability to generate them using a relatively simple cavity QED setup is therefore particularly significant. Perhaps the most exciting aspect of this discovery is what it suggests about the future of quantum engineering. For many years, progress in quantum technology has often seemed tied to increasing complexity. Building more powerful systems appeared to require more complicated hardware, more elaborate controls, and more sophisticated architectures. This work points in a different direction. Sometimes, powerful new capabilities emerge not from adding complexity, but from finding smarter ways to use the systems we already have. By making only small adjustments to a standard quantum platform, the University of Chicago researchers uncovered an entirely new landscape of entangled quantum states. The work remains theoretical for now, and experimental validation will be needed before practical applications become possible. However, researchers are already exploring collaborations to test the idea in real-world quantum laboratories. If successful, the discovery could help bring advanced quantum sensing technologies closer to reality while providing new tools for studying some of the most fascinating phenomena in modern physics. The dream of a universal quantum computer may still be years away, but discoveries like this demonstrate that useful quantum technologies do not necessarily wait for that future. Sometimes a simple idea can unlock extraordinary possibilities hidden in